So we're going to be talking about cyclohexane chairs. You probably approached this mean little bad boy in your organic chemistry class and you're thinking, what the heck is this? How do I solve it? Well, not to worry, because we're going to solve it together and figure out how to approach this problem. So here's a model of a cyclohexane. And I highly recommend using models for this problem, especially when you're first approaching it. So the cyclohexane, this isn't really in the chair conformation yet. Right now, it's in the boat conformation. And the boat conformation isn't as stable. It's a bit more unstable and more reactive than the cyclohexane chair. Right now, it's like a boat because you can like rock on the boat or whatever. To make it a chair, you just grab one side and you flip it down like that. And now this is where you rest your legs, and this is the head of the chair. It's like a chair. It looks like a chair when you see it from this side. And it's pretty cool because this is the most stable structure in all of chemistry as far as we know. Because maybe tomorrow we find something that is more stable. But as far as we know, this is the most stable. It has like zero instability. That's kind of crazy. That's pretty cool. That's like really, that's like very unlikely, but really cool. And you see these in nature all the time. And what they're doing is they're constantly flipping their rings. It's constantly going this way, and this one goes down, and then it goes back here, and then it goes like that. And it does that like 100 times per minute, which is pretty crazy. And it always goes back, and that's pretty crazy. So one thing that chemistry teachers like to do, organic chemistry professors, they like to do to torture you, is they make you do ring flips, and then you have to try to put everything back how it is normally. It's actually not that torture when you get the hang of it, and it's kind of fun when you get the hang of it. So let's get to it. One of the first things you should always do with this is numbering your carbons. Don't number them in like a way to do like nomenclature or anything like that. Just number them to keep track of them. You could even like assign them names like Bob, Joe, Mary. Just to like kind of, I use that as an example to kind of say like you could just, it's just, what matters is that you know in the end where it is. But a good tip to just kind of remain consistent all the time, the one that has the tip up, put that one 1, and the one that has the tip down, put that one 4, and then the rest you do it clockwise. 2, 3, 4, 5, 6. All right, so you got 1, 2, 3, 4. So another thing that you should keep in mind is that this one is just kind of like a branch. This is a branch, this is a branch. This is methyl, and this one is isopropyl. That's isopropyl, right? Yeah, I think so. 1-methyl ethyl. So, all right. So when you're this one, there's two kinds of branches that you can have. You can have axial, or you can have equatorial. Axial because it's on the axis straight, and equatorial because it's kind of on the side in like the equator of this thing. And you can see that. You can see like right here, this bad boy is straight up. This dude is kind of on the side. It's slightly pointed down, and this one is on the side and it's slightly pointed up, but they're still on the side. They're not like straight up like this guy. And there's two kinds of equatorials, as we saw. There's one that's straight up and one that's straight down. Equatorial up, equatorial down. When you do the ring flip, the equatorial changes to axial and the axial changes to equatorial. But equatorial, if it was up before, it's going to stay up. It'll just be axial, pointed up. And if it's if it was pointing down, then it's going to be axial but pointing down. So the direction of up or down stays the same for equatorial. It just changes the orientation of axial. So here, let's do the ring flip. Now the ring flip is basically this, but it's pretty much kind of like the mirror image in a way. You keep it like that, parallel, and you go down, and this one goes up. Now everything shifted one clockwise. This one is down now, so it's the tip down, and the 4 switched with the 1 in a way, and it's now the tip up. So you go 2, 3, 4, 5, 6. This 5 looks like a 6. Now it looks like a 5. All right, so isopropyl was axial up. Now it's equatorial. Which direction? Up. And when you draw equatorial, you want to kind of stay parallel to this other one right there. What's the other one? It's on 4. All right, so you keep that one on carbon. No, the next one is on carbon 2. So you keep it, this is why you number them, so that the branches stay on the exact carbons that they were and you don't make a mess. So the one on 2 is equatorial down. We want to make it parallel to this guy. Equatorial, no, sorry. Now it's going to be axial down. It's just down like that. And this guy is going to be, on number 4, it's going to be axial up. Since it was equatorial up, now it's just going to be axial up. And I put this double-headed arrow because it switches back and forth 100 times per minute. And that's pretty cool. And so you can use the model to kind of help you with that when you're trying to like form the structure. You kind of look at it like this, and then it's, all right, you remove them as necessary. You kind of picture it like this is 1, this is 4, up tip, down tip, and then you just switch it. So now it's the chair conformation, right? Yeah, and now it's switched around, up tip, down tip. And you can use that to help you out. And hopefully this video was helpful.